Okay, thank you very much for that really nice introduction, Randy. And before I begin, can everyone see my screen?
Yes, we can.
Oh, good. Okay.
We don't see it in presentation mode, though.
It is in presentation mode now. Is that helping?
Yes. Yep, now we see it. Perfect.
All right, great. Please feel free to interrupt me if you have any questions during the talk. And I'm just going to try to go slowly. And this is in largely the same talk I presented at AMS. I'd like to have done more analysis by now, but I haven't quite gotten to it yet. But I think there's a lot of interesting nuggets here that we can discuss. And then at the end of it, if there's interest, I was going to look at the web viewer for WAFS guidance for different forecasts during the time. So we could look at the evolution of the guidance in the viewer from different initialization times. So I'll look at the predictability aspects of, I like the Corn Belt Derecho term that you just used. And I just want to thank all of the co-authors. As you can see, there's quite a few of them. One thing that was neat about this is that we saw, the potential here after a really high impact event, and had a very long email chain between CIMMS and NSSL scientists and also SPC forecasters, and we're able to basically come up with the experimental plan for the WAFS forecast that I'll show later over email over the span of about a week or two. And so it was a nice broad team effort where we saw, a research opportunity and tried to make it happen quickly. Okay, I just have to click. I suspect everybody is familiar with the case, so I won't spend too much time going over the observational aspects of it, but certainly this is an extremely high impact event. It's the costliest single thunderstorm event in U.S. history. I had 7.5 billion in damages, but I believe that estimate has been increased possibly by several $1 billion. So it's, I think, by a lot, the costliest single thunderstorm event in U.S. history. And sadly, there are 4 fatalities and 1.9 million people lost power in 2 weeks. And this is just RGB composites of the synthetic aperture radar showing vegetation cover in Iowa before and after the storm, and showing just how extensive the damage to the cropland was. It's up over 20% of Iowa's cropland. And then, of course, another interesting aspect of this event is that the duration of the severe winds was so long, so there are portions of Iowa that experienced severe winds for nearly an hour. Okay. So that's a very, very brief overview of the impacts, and I wanted to just leap right into the observations. And so I'm going to keep this loop going, but this is a 19-hour loop of MRMS composite reflectivity from 03 UTC to 22 UTC on the 10th of August. And that's a time period that I'll focus on the most. And then I have local storm reports show up as they were reported in the animation. So you can see all of the blue squares across Iowa representing the extensive wind reports and the transition to more of a QLCS tornado event as you get into Illinois later in the event. And for the purposes of the predictability, I've tried to divide this loop into 4 different features and or periods that I think are of interest into how the CAMs handled it. So to begin with, I didn't time that well. I'm going to let it loop through one more time, but if you look prior to development of the derecho, you have this sort of multicellular convection in northeast Nebraska that's ongoing from maybe 03 to 09 UTC. And that ends up dying off before the derecho really gets going. So that's seemingly innocuous, but it actually does play an important role later on in how some of the CAMs predicted the event. The second one that I wanted to note was that you have elevated multicellular convection along the Nebraska-South Dakota border, and that is where this elevated MCS initially originates from. And that originates really in the 11 to 13 UTC timeframe. It gets going and moves into Iowa, and as it does, it becomes surface-based, and you start to see all the number of severe thunderstorm reports. So those are the time periods I'm going to look at mainly in this talk. We'd like to expand it to some of the QLCS tornado work later on, but for now we're going to really focus on the genesis of the derecho and how well that was predicted in different models. And just as a brief overview of the SPC forecast evolution, one thing I wanted to note is that SPC recognized the potential for this event is really quickly as the observations came in. But the story of the day, at least from the standpoint of a model developer, is in this SPC 0600 day 1 outlook, where they have a slight outlook across Kansas, Missouri, generally marginal in Iowa. And they say the main issue with this forecast is the difference in model solutions. So this is evidence that they were not getting really trends that they could trust from the available CAMs. And based on that, they went on, an observational or a broad consensus-based forecast for that. And then as soon as 0800 as a UTC, you started to get elevated CI along the Nebraska-South Dakota border, and they quickly recognized this and recognized that that fit better with the single CAM solution that seemed to predict the potential for an MCS or Boeing complex later in the morning. And so they note that possibility in MD. They then upgrade to a slight over all of Iowa by the 1300 outlook. And if you, even 40 minutes later, that you have a increasing threat for damaging winds and a new severe thunderstorm watch is going to be likely. So they've rapidly updated the potential severity of this event, and by 1630, they've now upgraded to a moderate as the derecho is really getting going, and they're using the word derecho in the outlook. So from a model developer standpoint, what's interesting about this is that it's an accurate forecast, but it's driven by the observations. So the science question is there an opportunity here to provide guidance that would have been more reliable from convection allowing models so that you would have greater anticipation of the potential of this event on the night before? And so that's basically what we're trying to answer. And for reference here, here's the HRF V2 probabilities of a wind gust greater than 30 knots in the 14 to 18 UTC period. So really when it was derecho genesis across Iowa during this time. And you can see you really have, even in broad neighborhoods, 10% probabilities of wind gusts exceeding 30 knots. So there's no clear signal here for a damaging wind event. If you look at the individual paintball swaths of winds, you can see that there are some members that are producing, more cohesive swaths of wind, but there's no consistency with the spatial location or even really the timing of those events. And so you'll note that one of them in brown here, that's the HER, does do quite well, but the remainder of the models are not predicting the event very accurately. And that's certainly not to say that the HER is better than the other models. That's just part of being in the ensemble, is that on this day, the HER happened to have a better solution, but on any other day, any of the other models could have had a more accurate solution. So based on this input from SBC and looking at the HRF probabilities, we wanted to try to run our Warn-On forecast system in a different, larger domain mode than we normally do, and for longer forecast lead times for the event. And we developed a domain to use that's much larger than what we typically use here, and that's shaded in green. Each of the blue dots with the circle around it are WSR 88D sites, and we're assimilating radar data from all of those throughout the event. And we're going to initialize the model at 01 UTC from the 0Z hurry, and then beginning at 03 UTC, run forecast out to 22 UTC with 18 members. So we'll have a 19-hour long forecast at 03 UTC, and then 18-hour at 4, 17-hour at 5, and so forth and so on. And what we're hoping to see here is that WAFS is unique in that it rapidly assimilates both satellite cloud liquid water path and WSR-88D observations every 15 minutes. And we think that does is it gives it an ability to more rapidly analyze individual thunderstorms within the domain. And if we are able to accurately analyze individual thunderstorms, the hypothesis is that we'll be able to accurately predict them for a short period of time. So this is sort of stepping out of our typical wheelhouse for WAFS, in that we're initializing forecasts before CI, and we're also going to run a much longer lead time forecast. So our expectations when we set this up is that we would see similarly poor forecasts in the early forecasts, but then once CI began, we'd start to see a rapid improvement, and would be able to latch on to the potential for a derecho earlier than what you would have gotten from other guidance. However, this is what we got when we ran it and we looked at the first forecast. So this is a 19-hour WAFS forecast initialized at 03 UTC. We're going to look at the ensemble 90th percentile values of the maximum wind gust. And so that's going to give us a reasonable worst case scenario for wind gusts across the region. And we're looking at output every 5 minutes, I think. And just for reference, the color table here, anything in orange represents gusts greater than 50 knots, so severe wind, and anything in red represents significantly severe wind. So I'm just going to kick this forward, and you can see the evolution of the event starting up here at the elevated storms in Nebraska. And you can see that it's predicting a really broad, intense swath of damaging winds that not perfectly, but pretty closely match did track of the eventual derecho. So this was an unexpected result, and that it was way better than we expected, especially pre-CI, because this is something that's doesn't really have the advantages that we think you can get in a WAFS forecast. There's no extra observations to assimilate to get it to latch onto the solution. So it opens up a lot of questions about why did it do so well. But on the plus side, it did really well. So there is a northward shift to the track of the derecho relative to the sort of the axis of the highest density of wind reports. And it's a little bit slow, but in general, for a 19-hour forecast, we think this is pretty good. And it's also represented, if you look at the these really light gray shading or the individual reflectivity pink balls from members, just about every single member predicted some variation on this derecho track. So it was a very high confidence solution as well. So that led to the question, which is, why are most members predicting the Iowa derecho? And what we're looking at here is it's a bit of a busy plot, but you have the shading underlying is most unstable cape, the ensemble mean of that, and then you also have the ensemble mean 700 HPA wind vectors and dew point contours in green, and then you can see reflectivity pink balls in 40 dBz. So what I want to show here is that you actually get this area of elevated cape that's moving northward in the early portions of the forecast, and then initiates convection along the South Dakota-Nebraska border about the time that it occurred in observation. So you get this accurate prediction of the elevated CI, and then that in turn leads to upscale development and an accurate prediction of derecho. So we thought that was pretty neat. And there is a northward error in the location of the initial CI, and that translates to the rest of the forecast, where it continues on as a northward displacement in the track of the derecho. And the other thing that I mentioned is, if you think back to that area in northeast Nebraska that we talked about, if you look at the pink balls here, there are certainly some in WAFS, but not a lot. You do not have a lot of upstream convection overnight in WAFS. You have really just the elevated CI along the South Dakota-Nebraska border, and then that leads to the derecho, and you have, very strong, most unstable cape throughout the warm sector, throughout the inflow region of the derecho. So one other quick note that we thought was neat is, if we look at the surface-based cape, you can see that the elevated nature of those storms, where there's no surface-based cape when they initiate. But you also look at, as they cross, in this case, the cold front and the axis into positive surface-based cape, you can see in a lot of the pink balls, a rapid southward expansion in the MCS, and you see it coincides with really a strong influx of severe wind reports. So we're getting, we think, an accurate prediction of the transition to being a surface-based system that's widespread damaging winds as well. So that's a nice thing to see in terms of predicting the severity of the event. The other one we were looking at, so we have this northward track. So are WAFS forecasts consistent in time, and are they able to improve on this initial estimate as you go forward in time? So what I'm showing here is simply the MRMS composite reflectivity at the time the forecast was initialized, to give you a sense of what observations are out there, what's being assimilated, and then the full probability swath of wind speeds greater than 50 knots using a 15-kilometer neighborhood. So that's a relatively small neighborhood compared to what you get with a typical next day CAM ensemble. They would typically use something, this is a 15-kilometer diameter neighborhood, so they would use an 80-kilometer diameter neighborhood. And so what it shows is all 18 members are predicting severe winds across Iowa, even 4 hours before CI. However, they are displaced northward. If you go forward 2 hours, you don't really have much CI, maybe the beginning of it in the Nebraska-South Dakota border, but you don't see a lot of change in the track of the storm. The WAFS becomes more confident in the track, but it's still displaced to the north. However, if you go to 7, actually through 7, it really doesn't change much at all. So, pardon me, I misspoke here. This is really the transient multicellular convection in Nebraska that was not maintained. And so that's not influencing the WAFS forecast very much. However, when you go to 09 ETC, now you've had the elevated CI, and you can see there's a notable southward shift in the track. And what that represents is it's better able to analyze the elevated convection, and it's still predicting it to go upscale, so you're getting a more accurate prediction of the derecho track in terms of you're removing some of that northward displacement. And after that elevated convection really gets going and starts to transition upscale by 11 ETC, now you're getting an even further southward shift, and you're really painting the highest probabilities of damaging winds over the maximum density of damaging wind reports. So you're getting a really accurate prediction of the derecho track at this point. And that's just a nice illustration, I think, of how rapid assimilation of radar and satellite data is able to correct errors in an initial forecast prior to CI and improve the forecast as you go forward throughout the day. Okay, so that's an overview of WAFS, and it turns out that WAFS has done pretty well. And so we also wanted to look at, why did other CAMs miss the event? And so what we went back to here is these are just href members, and I'm plotting just the composite reflectivity from them. And what I'm showing is the MRMS composite reflectivity in the upper left, and then the 03 HER composite reflectivity in the upper right, and then missile WRF and NAM nest here at the bottom. And I'll note that the missile WRF and NAM nest are representative of all the different href members besides the HER. So what I really like to do is compare the HER to the other href members. So this is at 03 UTC, and you can see that each of the HER, NAM nest, and missile WRF have spurious prediction of convection in northeast Nebraska. Going forward to 07 UTC, you can see that convection's expanded into a weak MCS in both the missile WRF and the NAM nest, with additional CI kind of occurring up in southeast Minnesota, southeast South Dakota, and southwest Minnesota here in the NAM nest. The HER is maintaining convection into Iowa, but it's a lot less widespread than the other models. And you'll notice at this point, you still have a reasonably clean domain of the actual observations. So you can see that these forecasts have all got varying degrees of error already in the evolution of convection, just in the first 7 hours that they've been run. And if you go through another 4 hours to 11 UTC, something that's encouraging is that all of the different models accurately predict the elevated convection developing along the Nebraska-South Dakota border. So the convection that eventually led to the genesis of the derecho is well predicted in each of the different CAMs. However, if you look at the area upstream of that, the HER is pretty clean with a couple of areas of spurious convection. However, you have a full-fledged MCS in eastern Iowa and the missile WRF, and kind of blotchy convection with some sort of complex up in Minnesota, but a lot more widespread convection in the other two CAMs. And as you would expect, with all this extra convection out ahead of the derecho, that has a very significant impact on the most unstable cape that's available. So looking at the HER cape, you have some evidence of cold pool from the spurious convection here in central Iowa, but in general, you still have significant values of cape throughout all of Iowa and over the entire track of the derecho. However, in the missile WRF, you've scoured out all most unstable capes, so you have just a stable environment ahead of the developing elevated convection, and you have something a little bit in between in the NAM nest, where you have really a large portion of western Iowa that's been pretty much wiped out, but you still have some higher cape levels out in eastern Iowa. And if you look at how this plays out, it would be about how you'd expect it to. This is now storm reports that are valid at 1700, so you can see, roughly the location of the derecho and observations there. And the HER has a remarkably accurate prediction in terms of the size and placement of the storm at this time. Whereas the missile WRF has mostly no storms in Iowa, there's no cape, and this sort of diffuse MCS is moving into Indiana at that point, and you have an MCS that's now moving into Illinois, Indiana, and the NAM nest, and really not a lot of convection in Iowa again. So the reason why the other CAMs have missed it is not that they didn't get the genesis mechanisms for the derecho right, it's that they over-predicted these multi-cell storms along the front early in the forecast period. So you have an error in the first 3 to 4 hours of these forecasts, and what that did is it really wiped out the ability to make an accurate forecast during the later periods. And that's a difficult problem to address because it was not an implausible solution. There were multicellular storms that developed along the front overnight in Nebraska. They just weren't maintained. So there's some sort of a very subtle environmental factor that caused those storms to decay in reality that did not decay in the models. And so if you want to have a well-tuned ensemble, you want to be able to address that uncertainty. So in some sense, the href forecast is not that bad. It's just showing you that it's very uncertain. But something that we would like to do is to be able to have higher confidence when you see these high impact solutions like what the HER provided there. And I sort of jumped the gun on the conclusions there, but the other thing I want to mention is that as for why WAFS did so well is it's not initialized straight from the HER, but the HER shares a data assimilation system with the HER. And so the initial conditions and boundary conditions for the WAFS are going to be very similar to the HER. So in this sense, WAFS was fortunate in that we initialized it off of the one CAM that did predict it well. So yeah, I just wanted to point out that something that may be a takeaway here is that it may be worth having multiple ensembles or more members to look at, because when you have a low confidence solution like what the tractor DI with Derecho would be, having more members to choose from may be able to provide a little bit more precision in the probabilities, where instead of saying, each one of the 8 members is predicting something different, you could say, well, 2 or 3 of the 16 or 20 members were predicting this progressive MCS solution across Iowa, but there's a lot of uncertainty in it. And so maybe you'd be able to start to get an idea that that is possible earlier than you would otherwise. And so that's something that we'd like to be able to show with the WAFS going forward. So in terms of future work, I didn't mention any of the QLCS tornado events. So that's something that a PhD student we're working with, Kelsey Britt, is going to look at. And so she's working with object-based verification code that is going to attempt to identify rotation objects within the broader QLCS and match that to azimuthal wind shear tracks or rotation tracks in MRMS data. So that project is just getting off the ground now, but she'll be looking at that in the year ahead. And we'd like to go back to the environment and try to diagnose factors that resulted in the overprediction of the frontal convection in most of the HRF numbers. And something that I think is going to be really important and looking forward to is we want to work with the SPC forecasters, where we want to go back and do a retrospective forecast using the WAFS guidance and look at, would this guidance have made a difference in the products that you issue? Would this have changed your thinking about anything and how? And try to document that. And so hopefully I haven't gone on too long. That is what I have to show, but I want to point out that I'm going to jump out of presentation mode. I also have the real-time viewer up, so I was going to look at a couple other things here. And if there are any questions or any requests for the viewer, we can just step through it. But I did want to show, during the Derecho, the WAFS member viewer, and show how different the solutions of all the different WAFS members are, at least in terms of the placement, size, and intensity of the Derecho. However, they're all consistent in predicting that it will happen. And so that opens up another can of worms in terms of talking about ensemble design, which is, this is certainly a reasonably large amount of spread in terms of spatial location and timing of the system. However, there's not a lot of spread in terms of, will this event happen or not? So you're sort of stuck where you have to figure out what's an appropriate amount of spread or uncertainty for this case when you look at the CAM ensembles, and that's a very difficult question. So thank you for your attention, and I'm happy to take any questions.
Thanks so much, Patrick. Absolutely fascinating presentation. Just an amazing event as well. So please raise your hand or type your question into the question pane. I know there's a lot of interest in this, so I'm sure we will have several folks chiming in here. Hey, Ryan asked about the link. Do you see did you see the link, Ryan? Did you get that?
Oh yeah. I'll put the link in chat, or I'll just go back to the presentation.
Perfect.
Did I see that?
So we had a question, Pat, from Phil Schumacher. He says, have you tried initializing with a different CAM, such as the NSSL WARF? If not, do you think using a different initialization would have changed WAFS performance?
We have not tried that, and it'd be somewhat difficult to do, because the nice thing about the Hurry is it actually is an ensemble, so we can just pull the members straight from the ensemble and initialize our ensemble. We'd have to perturb a solution like the NSSL work to generate an ensemble. But my expectation is that yes, it would change the quality of the WAFS forecast quite a bit. I'm betting that certainly before elevated convection develops in Iowa, you would get a much more similar ensemble forecast to the NSSL WARF from all WAFS members, where you'd have a poor prediction of the evolution of convection in Nebraska. One thing that I think you would see in the WAFS, at least my expectation would be, is that we do assimilate zero values of cloud water path and reflectivity where there are no storms. So we might see an ability to suppress the spurious convection as it's dying off in northeast Nebraska and begin to better predict the evolution or the potential for that derecho earlier than what would have been if we weren't assimilating those zeros. So we might be able to see some improvement before initiation of the elevated convection. But I think you would certainly see improvement after that CI of the elevated convection.
Okay, excellent. Mike Fowl has his hand raised. Mike, go ahead.
Hey, Patrick, hopefully you can hear me okay.
Yes, sir.
Okay, well, yeah, as Randy mentioned, I wish you would have had this guidance, obviously, in real time, but fascinating how well that it did, considering all the intricacies of this event. But my question is kind of related to a little bit what Phil had mentioned. So obviously this was an amazing reproduction here. I guess from a forecast perspective, have you done any work on essentially kind of a model climatology idea behind this? In other words, how rare were the values you were seeing in this event? In other words, I know during that period around this time, it was kind of a subtle forcing event, and each day there was models that were predicting some version of an MCS. How rare was this sort of a solution? In other words, could forecasters glean anything about not only is this the solution there, but what about the values of, say, 10-meter wind or that sort of factor? Have you looked into anything like that? Because I think that's maybe another target of opportunity that we could put in the hands of forecasters.
No, but that's a great question and great point. And I totally agree that, one aspect of this we have not looked at much yet, but would like to is, how does the severity of the WAFS prediction in this event compare to other MCSs that WAFS has predicted? And we don't have a large enough sample of cases to really do a proper climatology. We have 100 or so total WAFS cases to look at, but really maybe 15 with progressive MCS in them. I will say that anecdotally compared to other MCS events, this one and the July 19th, 2019 Wisconsin derecho are by far the strongest. Like they stand out in terms of the WAFS guidance relative to any of the other events that we forecasted. So that's a promising aspect of it, where it does seem to be picking up that this is a stronger than average event. I certainly don't think that it's going to predict the duration of the winds like we saw in reality, but it's at least giving some indication that this could be a high-end event. But looking more into the intensity forecast is something we're interested in doing. And to go back to your first point, another interesting research avenue that I think, and to be honest, I'm not that familiar with it, so I may be missing something, but I do believe that in general, CAMs perform worse over the summer than the spring because it's weakly forced. It doesn't have the same level of predictability to it. And so looking at a climatology of CAM MCS predictions just to get a sense of how common are the false alarms that you're talking about that you see every night, and what, if anything, is a useful signal in terms of early recognition of when the CAM may not be out to lunch and predicting an overnight derecho or an overnight MCS.
Yeah, thanks for that. Great question, Mike. I'm fascinated by the topic of, because having the M-climate and model climatology is extremely useful. So, we can look at M-climate QPF for the GEFs and based on reforecast, understand how unusual the precipitation forecast is for a particular event. And it seems like we don't really have the capability to do that with respect to CAMs because of the computational expense. But I wondered if there would be a way to catalog that sort of information in real time, as opposed to doing reforecasts. Like, what are the forecast values, like Mike was getting at, for wind speeds, et cetera, over a variety of CAMs or each individual CAM, as we go, and build up that climatology over the course of a few. It's not going to be like running a 30-year retrospective like we do at the GEFs or something, but it would be at least something to provide a little historical perspective on CAM, what a CAM is producing.
Yeah, I agree. I think that would be a really, really great research project. I think, they've done some work with that with the in-car ensemble, where Craig Schwartz and Ryan Sobash have published a few papers on that in the past couple of years. And then also using the long period that the missile WRF has been running, where you have a long enough period of the model running without changes in the configuration that you can create a climatology. One thing that it would be a little tricky, but I think that it could be done, is developing a climatology of HREF solutions, because it has been mostly stable for a few years and running every day. So there's certainly a lot of cases to draw from in that in the HREF to try to create a climatology.
Yeah, I think that would be such a tremendously valuable tool for forecasters. We have a couple other questions coming in. Ryan Sharp, Louisville asks, what are the plans to start up the WAFS again? What time frame?
I'm sorry, you cut out there. Could you repeat the question?
Oh, sorry. When is the WAFS going to start running again this season?
Oh, our goal for this year is to be ready to go in early April. Typically, we start at the beginning of the spring forecasting experiment, which would be roughly May 1st, but we'd like to get some more early season events this year, especially because we've missed really high-end tornado events in April in the past, and we'd like to be able to have the system running in real time for that and see if the guidance is useful. In the past, we've run over the summer in a collaboration with the WPC Met Watch Test, and we will not be doing that this year. So it is possible that there will be fewer real-time WAFS runs available this year, unfortunately. But we're hoping to use this year as a springboard towards developing WAFS to be able to run on the cloud and to be able to run without computational resources at NSSL as it does. And so we are hoping to use it as a period to develop it to be able to run more regularly in the future. But it will be running certainly from early April through the end of May, early June, and then hopefully on a case-dependent basis from then on, but not in a regular sense yet.
Okay, great. We have a comment from Jim Siebeking, Sue in St. Louis. He says, great presentation. One of my key takeaways is the importance of MetWatch and analysis. Seems like we are becoming too reliant on CAMs and forgetting pattern recognition.
Yeah, oh, sorry, go ahead.
Oh, go ahead, Patrick.
I can comment on that. I am a model developer, so I have to have a soft spot for the model solutions. But no, I completely agree. I think that using them in tandem is really the optimal way, which is the models are designed to provide useful guidance to forecasters, and so hopefully there are ways, and certainly with the observations is the quickest and easiest to tell when and where a model may be providing something useful. And just anecdotally looking at WAFs, the question comes up often about when is how do you trust a WAFS forecast when it's predicting a high-end event with a lot of confidence? And what we've seen in past events is to look at the environment. When you can look at the WAFS environment and it looks like it's accurate and it represents what you're seeing in the observations, then more often than not, that's a better WAFS forecast. If something looks like it's kind of weird in the observations or out of place, then that's a lot more chance for the forecast to bust. So I think observations and pattern recognitions are still indispensable, for forecasting, obviously, but also even in terms of I'm trying to do the right word to say this, but viewing CAM data with healthy skepticism, but being able to identify where it might be able to provide some value.
Excellent, and that point actually came up, Jim, in the AAR discussion that was kind of led from all your input, all the input from the offices, and Ryan Husted and Chris Guidro put together AAR, and that was actually a topic that is discussed in the AAR. So I see you just raised your hand, Jim. Ray Wolf, I'm going to unmute you because I know you've had your hand raised for a bit. So go ahead, Ray.
Thanks, Randy. One of the issues we face up here, Pat, is this nocturnal to daytime transition and how the CAMs are commonly poor performing in it. And I wondered if you've had any insight with WAFS, if it's doing a better job at catching this sort of transition, because this is an excellent case as to where that transition is obviously critical to the forecast of the day.
Yeah, it's a great question, and we're really excited to see that it did capture this, nocturnal to daytime transition and this elevated to surface-based transition. Unfortunately, I don't have a lot of insight to offer into that because we've never run WAFS in the early morning before this case, maybe for a tropical cyclone. But it's something that, as we are able to run WAFs, outside of our usual method, which is initializing it in the early afternoon and running it into the overnight, to be able to collect more data, to be able to look at how WAFs might be able to handle that transition. I mean, we certainly pay attention to the early evening transition a lot, but yeah, especially in these summer MCS cases, the morning transition is important, and I don't know of a lot of research that's looked into that. So there's an opportunity there to hopefully improve CAMs going forward by better learning about how well they're representing that transition.
Excellent. I think we have time for one more. Jim, you are unmuted.
Yeah, I just want to make sure you understood I wasn't coming across as I'm, con CAMs. Actually, I'm going to use your presentation here for my staff on how to use CAMs, how to properly use CAMs. So I think it's just, like you said, a combination of using the CAMs and the analysis and MetWatch to continually update the forecast. If you look at SPC's forecast, they were kind of slow on the uptake, given what you showed. That if the convection didn't develop in Iowa, then the HER was going to be probably more correct because there was more instability. So it was just kind of, I think your presentation really speaks to how to use it.
Thank you, I appreciate that. And I definitely didn't think that there was any, anybody coming down on CAMs. I know that they, like all models, they're all wrong, but they can be useful.
I was going to make the same point. This is Bruce. Patrick, that was just a phenomenal presentation. And Jim, you're spot on that. As much as we'd love a silver bullet, there's no silver bullet out there. And to me, what this presentation demonstrated, if I was in a Sue's shoes providing this training to a local staff, it's preparing them to be able to go down a couple of different paths based on real-time observations and what they're seeing. And in this case, it looked like there was sort of a bimodal approach that the models were taking, and it was all contingent upon how that lead convection evolved, or in this case, devolved. And the quicker that we can recognize those patterns and then connect it to the CAMs as to what is the most likely outcome, the quicker we can trend with our watch the warning gap type communication and ramping up for a change in how the convection is going to evolve. And I thought this case and what you presented, Patrick, did a phenomenal job demonstrating exactly that.
Thank you. And yeah, I couldn't agree more. That's if we have a good example of how observations can provide early indications of which CAMs to trust more out of this case, then that's I'd be thrilled with that result.